In this lab, we are observing a falling object. So the purpose is to observe the falling object and be able to model it to Newton's second law. Computational models were created to compare the actual results with theoretical results. Newton's second law was used when examining the motion of a speed. This law states that the net force acting on an object is proportional to its mass and acceleration. Tracker was used to collect position and time data from the experimental video, and GlowScript was used to create computational models of the object's motion. The position versus time data of the object created a nonlinear graph with an increasing slope, suggesting that the object experienced an acceleration. And the experiment in code, we have the system as the crumpled paper, the surroundings as everything else around it, including the air, floor, hand, ruler, etc. And then we have initial conditions at time equals 0 to be 0, 0, 0 for the velocity, meters per second, and then the position was 0, 0, 0 meters. And it traveled a total distance of 1 meter with a time from release to hitting the ground to be 0.467 seconds. For our coding, the first thing I edited was the mass of the ball, which was measured to be 3.4 grams. The next thing that was edited were the initial conditions, and these were made to be 0 and 0 for both position and velocity. Following the Newton's second law equations were edited to be more general. So those are these two lines right here. And the net force for the model that just included the force of gravity was just this weight, which was defined by this line of code. And then with the model that included drag force, we added drag force to the net force equation and defined drag force in this line of code. Our time was edited to be 0.467 seconds, and our B value was determined through the empirical method where we guesstimated and ran the code several times. Here we have a couple graphs, a couple data sets. So in terms of physics errors, our model with gravity and drag force is in yellow, while our experimental is in blue. So over here, the line, they have the same starting point, same ending point, our more reliable model compared with our experimental, but our experimental data has a steeper slope. The model drag force was greater than the actual drag force. So that's physics errors. And then we have a video of the model with Fg as the net force acting on the object predicts the object to fall a greater distance than actually observed. Without drag force, the object would have been able to fall a larger distance in the same amount of time. The experimental slope is steeper than the slope of the model with Fg and Fd. This might be because the drag force acting on the object was smaller than the computational value of the drag force. Some possible sources of error include that the paper ball might have fallen too fast, resulting in unreliable data, and then the calibration of the experimental video and tracker might have been slightly off, depending on which might have just affected accuracy. Neither model predicts terminal velocity within the change in time. Both models show velocity time graphs with a slope of some value, meaning that the object is experiencing an acceleration the entire time it falls. So the object just didn't fall for a long enough time for terminal velocity to be reached. And then when an object experiences terminal velocity, then it has a net force of 0, since drag force and gravitational force cancel each other. And the terminal velocity would remain the same if the object was given an initial downward velocity, it would the object would achieve terminal velocity at a different time, and it would either increase or decrease speed depending on how fast it was launched.